Okay, for this portfolio, we've already calculated the geometric mean return, and we've calculated the arithmetic mean return. So we can do the same thing for the benchmark. Now, remember, for the benchmark, we have the returns given, but not the values of the benchmark. So a benchmark could be some type of index or a combination of indices, or it could just simply be something else. But we want to compare our percent return with the benchmark percent return. And remember that these returns came from these values. If we have a benchmark that's like an index, the S&P 500 or something like that, we would simply start off with the same values for the index and then calculate the percent returns for that index or whatever benchmark we have. So for right here, we have the benchmark returns, and we would like to calculate the geometric mean and the arithmetic mean returns for the benchmark. So the simple arithmetic mean is easy. Is simply the summation of these returns here, and then we're going to divide by 5, and that would give us our simple mean. So if we look at it, we generated on average 3% per year. The benchmark generated 2.9% per year. So we could say we beat the benchmark over this 5-year period. Now, what's the geometric mean? You may remember from a previous video that there are 2 ways we can calculate geometric mean. One of those ways is simply looking at the difference, the percent difference between the beginning value and the ending value. That would give us the percent change from these 2 values for that entire period, in this case a 5-year period. And then if we wanted to calculate the yearly geometric mean or average, we would take the 5th root of that. We can't do that with the benchmark because the benchmark doesn't have these values. So what we have to do is calculate it the second way, and that is take the compounded return over the 5-year period for the entire 5-year period using these individual annual returns. So how do we do that? Well, we're going to add a 1 to each one of these and then compound those. So I'm just going to bring it off over here so we can see what we're doing. Just like what we did over here with this geometric return, equals 1 plus that particular benchmark return. And again, I'm going to get rid of the percent, have that go all the way down. I'm going to take the product of this right here. So I can say equals product. I'll go ahead and do that since we already know what we're doing. We're simply multiplying all of these together. 1.152166. When we take away the 1, we know that that is 15.22% over this 5-year period. That's for the entire 5-year period. But we would like to know what the one return is per year for each of these 5 years that would give us this 15.21%. And we do that by then taking this right here and taking the 5th root. Notice that will give you 2.8. We take away the 1 to isolate the rate. And our geometric mean return then is, as a percent, 2.87. So I'm going to move that over here and say that's 2.87. And again, remember that our geometric mean will be smaller than our arithmetic mean to make room for the compounding. And now we want to look at our relative return overall. How did our portfolio performance compare to the benchmark performance? Well, notice that for the first year we made 1%, the benchmark made 2%. The benchmark did better, so we underperformed our benchmark. We could just simply say that 1% minus that 2% gives us that 1% underperformance. Here we also underperformed by 1%. We lost 2%. The benchmark lost 1%. We lost 1% more than what the benchmark did. We also underperformed here by that 0.5%. But here we started to beat the benchmark. We beat the benchmark this year and we beat the benchmark this year. So these are our individual annual relative returns, the returns that are the difference between our portfolio return and the benchmark return. And the geometric mean return really wouldn't have any significance here for this relative return. What we're going to do here for the relative return is calculate the simple average. So again, we add all those and then divide by 5. I just moved that formula over here. And so on average, we outperformed our benchmark on a per year basis by 0.1%. Again, we have to consider the compounding effect there, but for our purposes, we're only looking at that geometric mean. We outperformed the benchmark by 0.1%. Now let's look at standard deviation. Remember that standard deviation is a measure of volatility. We're measuring the volatility or fluctuation of these individual returns around this mean return. So on average, we did 3% per year, but notice in year 1, we were 2% below that. In year 2, we were 5% below that. In year 15, we were right on it. In year 16, we were 2% above that. And in year 3, we were 5% above that. So we have a lot of deviations here, individual deviations. The idea behind this is, well, what's our average deviation? Now here's the problem. Let's go ahead and calculate these deviations that I just mentioned for each year. Let's say equals 1, that 1% minus the 3% there. I'm going to lock that. So we underperformed on 2013 by 2%. And then we go ahead and bring those down. As I said before, for the second year, we underperformed by 5%, and then we did the same as our average, and then we not outperformed, but we did better than the average this year and better than the average that year. And so we have a lot of deviations here, and it's all right to see this with 5 years, but what if we have 60 months, or what if we have 20 years? It's hard to get an idea of how volatile our performance was around this mean. And so what we'd like to do is take the average of these. It makes sense, right? Here are our individual returns. Well, what did we make on average? It's a measure of central tendency. We did 3%. What about here? Well, we have all these deviations. What did we do on average? Notice this. I'm just going to copy our average formula over here. If we add all those together and divide by 5, what do we have? We have 0. Why is that? Well, because if we add all these together, just take the summation here, boom, all those equal 0. The negative 2 cancels out the positive 2, the negative 5 cancels out the 5, we're left with the 0. So we got 0%. And why is that? Because these deviations are deviations from the middle. And so we have all the negatives canceling out the positives of equal weight. And so we just can't take the average of the deviations. There's 2 ways around this. Number 1, we can take the absolute value and just say 2 plus 5 plus 0 plus 2 plus 5 divided by 5, and that would give us the mean mean absolute deviation. We're looking at the absolute, but there are some problems with that. Because we are just arbitrarily saying that negative 2 is no longer a negative 2, it's a 2. So what we would like to do is transform each of these deviations in a natural way to then come up with some type of average. And we're going to do that by taking the square of each of these deviations. So we're going to say that the negative 2 times a negative 2. And notice if you have a negative, that's not in dollars. We want to put that in. Let's just look at this as general. Notice that when you have a negative multiplied by a negative, you have a positive times a positive is a positive. So what we have here, this column here are squared deviations, and all of those are going to be positive. Now what we can then do is calculate the average of those squared deviations. But before we can just do that, let me explain here. There's a difference between, and hopefully you recognize this or remember this from your quant class and other courses, that there is a sample standard deviation and there is a population standard deviation. It applies also to the variance. If we say the squared deviations divided by n, that would give us a population variance. If we say the squared deviation, the sum of the squared deviations divided by n minus 1, that gives us a sample. And so here, really this is just a sample of different returns that we have for our portfolio. So what we're going to do is we're going to add all these together and divide by n minus 1. So let me bring this over here. And so what we have here is we have the summation of those divided by not by 5, but by 5 minus 1. Or I just put 4 there. And so that gives us, and let me just put that as a decimal. This right here is the variance, the sample variance. This number here is a result of squared deviations. And so the bigger the number, the bigger the variance, the bigger the volatility, but it really doesn't mean too much to us. To put it back into our original units of percent, we would like to take the square root of that. We put squares in each of these. We squared each of these. So in order to take the square out, now that it's accomplished what we wanted it to accomplish, we're going to take that square out. So we're going to take the square root of that particular number, which is raising it to the 1/2 power. And so our sample standard deviation is 3.807%. I'm going to go ahead and put that as percent and move that over here where that's supposed to be. Okay. Now, we can do the same thing for the benchmark and find the standard deviation for the benchmark. What I want to do is equal standard deviation dot S. That's for the sample standard deviation. And I'm going to calculate the sample standard deviation for those right there. Same process, but we're just using an Excel function to do it real quickly. So notice that we have, we did better than our benchmark. We made 3% on average per year. Our benchmark did 2.9% average return per year. But notice our standard deviation. Our standard deviation, the volatility that we experienced in our portfolio, was larger than the volatility that the benchmark experienced. Now, the standard deviation here in volatility variance and a standard deviation as a measure of volatility is a measure of risk. And why is that? Let's see if we can figure that out. Let's go back over here to a whiteboard and hopefully I can explain it for you. You start off here with the original amount and notice that let's just say that an asset or an investment can go up or it could go down. I might better give myself more room. It has two options. Of course, it has an infinite number of options in reality, but let's just say this is what the asset can do. It can go up or it can go down. And then once it goes up, it also has another two options in the second period. It could go up or it could go down. And each one of those means it could go up, it could go down. It could go up, it could go down. And so you get the idea. Up, down, up, down. Each one of these, we're just continually branching off the trees. Now compare that with an asset that is not as volatile. In other words, it could go up, it could go down, but the difference here, the volatility, let me maybe, the difference there is not as wide as this one right here. And so it still can go up and down, but it doesn't, each period, its standard deviation is smaller. So it would, oops, I think I redid that one too much. It doesn't fluctuate as much. And so if you look at the spread of that investment compared to the spread of that investment, and then you look at a particular mean return, but just think about this. look at the, let me extend this out. Look at the range here of possible outcomes compared to the range of possible outcomes here. And the reason why we have that is because of this fluctuation, individual fluctuation. The larger the standard deviation, the larger the volatility, then the more, the wider the range of possible outcomes are going to be over here. So hopefully we see that the larger the volatility, the more uncertain we are of where our end values will be for an investment. So that's why volatility is a measure of risk. And in this case, we're using standard deviation as a measure of risk. I had to go over here and fix this information over here. Whenever I deleted the data over here, these equations were linked, and so when I deleted that, you may have noticed these turned to, some of these went goofy. This is like 100%, I think, and this one was 0. So I went ahead and fixed that, and so now we can move on and look at risk-adjusted measures. Let me look at show you a particular illustration here, hopefully that will help. We have, let's look at our example here of a 10% return for A, and let's say a 10% return. No, let's look at a make it a 20% return for B. So now we're looking at percent changes. We would say, oh, B did a lot better, but we have to ask ourselves, did it do a lot better because of risk or because it was just better performance? Because we have that caveat, you know, that maxim there that says the greater the risk and the greater potential returns. And so if you're earning a greater return, it's probably because you've been exposed to greater risk and not because you're a super duper investment manager. So let's look at the risk here. And the risk that we've looked at so far is standard deviation. We're also going to be looking at beta or systematic risk as a measure of risk. But let's say, for instance, that we have A had 10% return, but its standard deviation was 5%. Well, notice here that A gave us 2% return for every 1% standard deviation. Okay. What about B? Well, if B had a standard deviation of 10%, B also did 2% return for 1% standard deviation. So on a risk-adjusted basis, they're similar. A gave you 2% for the level of risk that you took, and B gave you 2% for the level you took. Now, if this were 25, let's say, okay, then B would not give you 2%, but 2.5 for every 1%. Then we can say B outperformed A on a risk-adjusted basis. It gave you more return per its level of risk. And so when we're comparing returns, and in this case, we're looking at our portfolio and the benchmark. Or it could be between two portfolios as I did here. We would have to look at how much return we got per level of risk. Or if we want to compare them, what we would do is, let's look at this again. We've got A and B, especially when we get down there to the M squared. We have A gives us a return to risk of 2%. Well, let's go back to the original. We have 10% per 5% standard deviation, and this one is 20%, going back to the original example, given 10% standard deviation. One way we can do that is simply adjust this return to reflect if this standard deviation matched that standard deviation. So in other words, if A were just as risky as B, what type of return would it get? Well, A is half as risky as B, so that means we need to double it. So A's return that's comparable to B that would make the standard deviation the same. In other words, let's just say, let's not make A 5%. What if A had a standard deviation of 10%? Well, we know that for every 1% is getting 2% return, then A's return would not be 10%, but it would be 20%. And then we can compare these two. Now these two are comparable because the risk level is the same. So let's look and see how this goes through with the calculations over here. We'll first look at the Sharpe ratio and the Treynor ratio. The Sharpe ratio is looking at the measure of return given a certain level of risk that I mentioned before. But in this case, and let me go ahead and write this formula down for you here. The Sharpe ratio is, can't write with my eraser. We're taking the return of our investment and then we're subtracting from it the risk-free rate. And you may notice down here, oops, risk-free. I have the risk-free rate down here, 1.8%. Why do I want to do that? Because here I'm isolating the amount of return that's based on risk. If this investment had no risk whatsoever, it should earn the risk-free rate. And I'm measuring the amount of return it's getting for its risk, so I want to look at its risk premium. So the rate or the return that the portfolio is getting minus the risk-free rate gives me the return based on risk, its risk premium. Divide that by its measure of risk. And for the Sharpe ratio, it's going to be standard deviation. Or in this case, that's the population standard deviation. We know from stats that the sample standard deviation is like a little s there. And so we can calculate the Sharpe ratio over here. And we take that average return of 2.99%. Now let me check on that rate. Where does that rate come from? Had to go back and fix some things. There was some things just a little bit off when I adjusted those figures last time. I believe these are the same figures we looked at before. We have the geometric mean, the arithmetic mean, standard deviation. Sharpe ratio. So let's continue on with the Sharpe ratio. That's equal to, I'm going to put this in parentheses because I'm going to be dividing here, that arithmetic mean minus the risk-free rate. And let me do this step by step. So in other words, this portfolio made 1.2% above the risk-free rate. So that 1.2% is based on the amount of risk that we took. Okay, what risk did we take? The Sharpe ratio uses the standard deviation as a measure of risk. So we say it made 1.2% return based on that much standard deviation. So the Sharpe ratio is 0.3151. And that tells us that this portfolio made 0.3151% for every 1% standard deviation. We can also do that with the benchmark, and then we can compare the two. Which one did, now before we do that, remember, our return was larger than the benchmark return, but our standard deviation was also larger than the benchmark return. How does it measure? Did we do better on a risk-adjusted basis? Was our return per level of risk more or less than the benchmark? Let's see. Well, here, notice the benchmark, the benchmark really outperformed us. What do you mean, Alan? We did 3%, they did 2.9%. Yeah, but they got more return per level of risk. The benchmark squeezed more return per level of risk than we did. For each 1% level of 1% standard deviation for us, we only made 0.31% or 0.32%, while the benchmark made over 1%. So on a risk-adjusted basis, the benchmark outperformed, or we, put it this way, we underperformed the benchmark. Now, the Treynor ratio is just like the Sharpe ratio, but instead of calculating, or instead of using standard deviation as a measure of risk, we're going to be using beta as a measure of risk. And you may know I have beta down here that's blank, and you can calculate beta using these numbers up here. It's usually, we should be using something more than 5 periods to calculate beta, and that's beyond the scope of this video. So let me go ahead and retract and find a beta for it. And here we go. I've input a beta of 0.67. There's the exact one, just using these 5 periods. Again, we might not want to do that using just 5 periods, but our beta is 0.67, and that's a measure of of our systematic risk. And so the Trainer ratio is exactly like the Sharpe ratio, but it's using beta as a measure of risk. So we'll go through the same process. Equals, we have the arithmetic mean of 3% minus our risk-free rate. That's our return based on the level of risk, and the divided by not standard deviation, but by beta. Okay, that is 0.02. Now we can bring that over to the benchmark. There's one thing about the benchmark. Our benchmark, by definition, the beta for the benchmark is 1, because this beta here is a measure of the relative volatility of the investment to its benchmark, or to the market if you're using the market as the benchmark. And so this will always have a beta of 1. So for this one, to calculate the Trainer ratio for the benchmark or for the market or a particular index, it's simply equal to its arithmetic mean minus the risk-free rate. Looks like it's going to be kind of close here. So notice what we have here. Who did what? On a market risk adjusted basis, we did better. So notice that notice this, we did 3%, the index did 2.9%, but we were actually less risky than our benchmark on a systematic risk basis. And because of that, our Trainer ratio is larger than the benchmark's Trainer ratio. So did our portfolio outperform or underperform the benchmark? It depends. If you're just looking at it from an absolute return basis, yes, we did. If you're looking at it on a risk-adjusted basis using standard deviation, we did not, looking at the Sharpe ratio. We did looking at systematic risk. And so it depends on the preference of the manager. Now for a portfolio, we could argue that the portfolio is a diversified set of assets or securities. And so because of that, its relevant measure of risk should be its systematic risk. Now let's move on toward the information ratio. The information ratio is a measure of risk in relation to the benchmark. Notice the relative returns we have over here. An investor has invested in this particular portfolio that is of the same characteristics as this benchmark. And that's why this whatever the benchmark is, S&P 500 or a blend or what have you, that's why the benchmark is chosen. So any deviation too much from the benchmark may indicate that the style or the investments in this portfolio are not actually reflective of the benchmark. Now, obviously, we would like these relative returns to be as positive as possible. If we're a passive investor and we're trying to match this benchmark, then these relative returns here should be small. If we're an active investor, then these returns here should be large. And so we're either trying to match that benchmark and have these small, or either we're trying to beat the benchmark and have these large. If that's our objective, then it's not our risk. Then is not necessarily the risk or the volatility of these individual returns here, but the volatility of how our returns compare to the benchmark. That's why it would be important to calculate the standard deviation of these relative returns here. So we can go ahead and use our formula to calculate standard deviation using the sample, and we're calculating the standard deviation here. Now what's that going to tell us? That means that the lower the standard deviation, the more certain we're going to be of hitting that arithmetic mean. If we're an active investor and we're trying to generate alpha, and we'll get down here to Jensen's alpha here in a moment, but if we're trying to generate those excess returns, we're trying to beat the market. But think about this. If we have a good arithmetic mean, but we have a large standard deviation down here, that means we're exposed to a lot of risk related to that extra return. So we would like this standard deviation down here to be small as well. That way we're more sure about getting that mean relative return. So here's our mean return, and here's our standard deviation. What the information ratio does then, it looks at the amount of mean return per level of risk standard deviation, somewhat like the Sharpe ratio and the Treynor ratio. So it's simply going to be that mean relative return divided by that standard deviation. That standard deviation of those relative returns is called tracking risk or tracking error. And so the mean return divided by the tracking error gives us the information ratio. And we would like that information ratio to be as large as possible, obviously. The greater the mean return, given a smaller level of risk, to generate that excess return there. And we can that's really used if we want to compare ourselves against other managers. Are we a good manager or not? Well, if we have one manager that has a consistent information ratio of 0.5 or 1 or 1.5, then they're doing a lot better than us who just generated 0.075. Now, let's go on and look at the capital asset pricing model rate. The reason why we have to generate that is because we want to come up with Jensen's alpha. Let's look at this here. What Jensen's alpha does here, look over here, Jensen's alpha. What Jensen's alpha does here is says the return of the portfolio minus the return of what it should be. Given its level of risk. So how can we calculate the return of the portfolio given a certain level of risk? Well, we can use that using the capital asset pricing model. And what's the capital asset pricing model? It says that the return on an asset is equal to the risk-free rate plus the asset's beta times the market risk premium. And what's the market risk premium? The market risk premium here is the amount of return the market is getting based on its risk. So it's simply the market return minus the risk-free rate. Beta is the beta of this particular asset, I, so we can signify it that way. And what that means is if this stock or this asset were as risky as the market, as its benchmark, then it would have a beta of 1, and therefore it should get the same risk premium as the market or the benchmark. Add that to the risk-free rate, and that would give us the entire return. If this particular asset were riskier on a systematic risk basis than the market, it would have a beta of greater than 1, and likewise, if it were less risky, a beta of less than 1. So in this particular case, we have a risk-free rate of 8%. This asset needs to generate at least 1.8%, and it needs to generate at least 0.67, here's our beta down here, it needs to generate 0.67, at least 0.67 of our benchmark's risk premium. So here our market return is the 2.9%, and the risk-free rate is 1.8%. Let's go ahead and plug that in. So cap M equal to the risk-free rate. We need to generate the 1.8%, plus we need beta times the benchmark's risk premium. What's the risk premium? It's the benchmark return minus the risk-free rate. 2.54%. So based on the systematic risk of our portfolio A, we should have generated 2.54%. What did we generate? 3%. So our alpha is that 3% minus the 2.54, 0.46%. So we generated excess returns there. Now notice here, if we just look at the absolute returns between our portfolio and the benchmark, what do we have? We generated 3%. Our benchmark generated 2.9%. So we beat the benchmark by 0.1%, but that's not on a risk-adjusted basis. That's 0.1% more than the benchmark, but we were less risky down here as signified by, as indicated by beta. We were less risky than the market. If we were to, what return should we have generated if we were basing our return on this risk level? We should have gotten 2.54, but we got 3, you see. So we generated an alpha or an excess return beyond the return we would expect based on risk by 0.46%. Going through it again, this right here, the geometric means and the arithmetic means, that's just looking at the absolute returns there. I mean, just the standard returns without regard to risk. And then we can compute risk based on standard deviation or this beta here. And then we can compare returns or adjust these returns, the performance, by the standard deviations to get the Sharpe ratios, or beta to get the trainer ratios. And we notice that we underperform based on Sharpe, based on standard deviation, and we outperform based on beta or systematic risk. And then we looked at the information ratio, which looks at the amount of return we get per level of volatility for our relative returns. And then we looked at Jensen's alpha, which gives us the amount of extra return we got per level of risk using systematic risk. And then M squared, we adjusted our risk level or standard deviation to equate that with the benchmark, and then compared the returns here with the regular arithmetic mean of the benchmark.